Let us make a quick revision about the very basic concepts in our chapter of interference. The basic experiment in interference is the Young double slit experiment, in such a way that if we have a card, and in this card, it's an opaque card for sure, not transparent one. If we have two slits, this is a slit S1 for example, and this is a slit S2, and the distance between them A is very small, in the order of 1 millimeter for example, and here we have a screen. If we have a light, suppose a laser light, this is a laser source emitting a beam of light. Once this beam of light strikes the slits, each slit becomes as a secondary source, and light diffracts from this slit. Diffraction takes place here from slit S1, and diffraction takes place here from slit S2. And on the screen you notice that the diffraction pattern from S1 and the diffraction pattern from S2 overlap, and here we obtain a region, a very important region called interference region. By interference we mean interference of the diffracted wave from S1 and the diffracted wave from S2. We have an interference region between these two diffraction patterns or diffraction waves, and on the screen we will obtain the interference phenomenon pattern here on the screen. Along this line here we'll obtain we will obtain here the interference diffraction pattern, in such a way that we will notice at this position a bright fringe, and here another bright fringe, another bright fringe, another one, and on the second on the other side from this position we will obtain another bright fringe, another one, etc. And between every bright and bright we will have a dark fringe. This is a dark. So we will obtain an alternative bright and dark fringes. The important thing I have to remind you about is that for this interference pattern, this is interference pattern. For this interference pattern to take place, to exist, the two sources, S1 and S2, must act as, number one, coherent sources or synchronous sources. And number two, they must act as coherent sources. By synchronous sources I mean that F1 must equal to F2, and this is very easy to obtain. The frequency of the wave emitted by S1 must be equal to the frequency emitted by the frequency of the wave emitted by S2 in order to call S1 and S2 as synchronous wave. And this is very easy because the wavelet or the source S1 and the source S2 initially they belong to the same wavefront coming from the laser source. So the frequency here and the frequency here are the same because they belong to the same wavefront from the laser source. Therefore, this condition is very easy to obtain. But the problem in the second condition, Coherent sources. What do we mean by coherent sources? By the way, in case of laser source, the two sources S1 and S2 are coherent. But I'm going to speak in general. What do we mean by coherent sources? Forget for now, forget that I'm speaking about laser sources. Let's speak about ordinary light source. Suppose here we have S1, slit S1, and here we have slit S2, and here we have the screen, and here we have an ordinary light source. Suppose we have an incandescent lamp. Incandescent lamp that emits a certain radiation, suppose blue light. Okay, blue light of constant frequency. This means that S1 and S2, when they emit their diffraction patterns, this one has frequency F and this one has frequency F. F1 and F2 are equal here because the light is blue and it has constant frequency. So the synchronous the synchronity or S1 and S2 are synchronous anyway. So the first condition is satisfied here. But what about the second condition? By coherence, we mean that at the same instant, the wave emitted by S1 and that emitted by S2 have a constant phase difference. How this could be attainable? Let's return back to our source, which emits the blue light. This is the screen here, and I have said before, this guy emits blue light of constant frequency. Therefore, S1 and S2 acts as synchronous sources. Suppose this is an ordinary light bulb that emits blue light. Suppose at instant t1, the wave emitted from S1 is of this form and the wave emitted by S2 is of this form. You can notice here that the wave at S1 and the wave at S2 starts from the same position, so they are in phase. Accordingly, wave 1 and wave 2 are in phase. Therefore, the phase angle between them, I'm going to call it phi, suppose, the phase angle between them is 0. Therefore, once these two waves reach this point, suppose I'm going to call it P, point P, they will reach point P in the same manner. Suppose the first wave reach point P as crest, and since these two waves are in phase, therefore wave 2 will reach P also as a crest. Accordingly, at point P we have a crest plus another crest. Therefore, we will obtain two crests interfering. Accordingly, we will obtain a large crest, and this is called constructive interference. So at point P we will obtain a bright fringe because we have a constructive interference. Therefore, you have to save in your mind that at point P right now we will obtain a bright fringe. If these two sources still act as two sources with the constant phase angle phi equals 0, therefore at any other instant the point P will still a bright fringe. What do we mean by this? Suppose after a certain instant or at another instant t2, right now I'm speaking to another instant t2, at another instant t2. At another instant t2, suppose instead of the wave, instead of being like this, the wave, for example, will be like this. Suppose it's right now like this. And since the two sources, as I have said before, in phase, therefore this guy will be like this. Here S1, or the wave starts from this point, and here S2, or the wave from S2 starts from this point. You can notice that they start from at the same instant from the same position. Accordingly, they will reach point P also the same. Suppose from S1 we will obtain a trough here, and from S2 we will obtain also a trough. Therefore we have a trough added to a trough, and we will obtain a larger trough. Therefore I obtain constructive interference again, and the point P still behaves as a bright fringe. This is because the phase difference was 0 and this is still 0. Hence the point B was bright fringe, and it's still bright fringe, and will still bright fringe forever. But what happens if the phase difference is not constant? For example, this is my bulb. That emits this is the screen. This is the bulb that emits blue light, as I have said before. Suppose that the phase difference between S1 and S2 is not constant. What do we mean by this concept, or by this term is not constant? This means that at a certain instant t1, I'm going to draw what happens at instant t1 with thin color or with thin pen, and at instant t2 I'm going to draw what happens with thick pen. Okay, let's move back to the instant t1. At instant t1, suppose, for example, first the wave starts from S1 like this, and the wave starts from S2 like this. You can notice here that the phase difference, I'm going to call it phi 1 because this is at instant t1, was 0. And assume that this is my point P on the screen here. Suppose that the wave coming from 1 reach as a crest, and the wave coming from S2 reach also as a crest. Therefore we have a crest added to a crest. Accordingly point P, we will obtain on point P constructive interference, and therefore point P is a bright fringe on the screen. This is at instant t1. Assume that at instant t2, suppose S1, the wave from S1 starts also like this, but the wave from S2 starts like that. Why this happens? Because the bulb is not emitting waves at constant rate or in a coherence pattern. So the wave reaching S1 and S2 right now are out of phase. Therefore the phase difference between them is pi radian, in such a way that if this was at a crest, this is at a trough. Accordingly here, suppose the wave traveling from S1 reaching P as a crest, and that traveling from S2 and reaching P will be a trough. Therefore here we'll obtain crest added to a trough. They will give us 0 result. Accordingly, we will obtain a destructive interference, and P, instead of being bright fringe, it will be a dark fringe right now. Therefore, if the waves emitted by S1 and S2 are not coherent, the points on the screen, or the interference pattern on the screen will not be stable. What do we mean by stable interference pattern? Stable interference pattern is the interference pattern in which a bright fringe remains bright fringe and a dark fringe remains dark fringe. The bright fringe remain bright fringe and the dark fringe remain dark fringe, etc., etc. This is a stable interference pattern. But if the interference pattern is not stable, this means that the point that was acting as a bright fringe may act as a dark fringe at another instant, and so on. Therefore, as a conclusion and as a closure, to obtain a stable interference pattern on the screen, a very important condition must be satisfied, which is the two sources S1 and S2 must be coherent. So, to obtain interference in general, regardless with the stable or unstable pattern, to obtain interference, the two sources must be synchronous, that is, have the same frequency. But to ensure that this interference is stable, another condition must be satisfied, that these two sources must be coherent. Accordingly, to obtain stable interference pattern, we have two conditions that you have to remember: that the sources S1 and S2 must be synchronous and must be coherent at the same time. This is what I have to speak about synchronous and coherent sources in interference, in Young double slit interference experiment.